So it turns out back here I actually had a mistake in my second derivative. I didn't watch the sign correctly. So f prime of x is actually 3x squared minus 20x. And the second derivative should not be 6x plus 20, but 6x minus 20. So the derivative of 3x squared is 6x, and the derivative of negative 20x is negative 20. So again, the question is concave up or concave down. And our answer to that lies in the fact that back here we determined that at f double prime of x, that is where there's a change in concavity. So how do I do that when my function is not my second derivative is not a constant, but instead it's a function? Well, it's much like the first derivative. If this is a function of x, then I can ask the question of when does the second derivative equal 0? Okay, so that means I'm going to set my second derivative equal to 0, and I'm going to solve 6x minus 20 equals 0. So that means I'll have 20 equals 6x, and I'll have x equals 20 over 6, which is approximately 3.67. So what this is telling me that I potentially have an inflection point, or a possible inflection point, call that as an IP for inflection point, at x equals 3.67. So what I'm going to do is I'm just going to draw a number line here, and I'm going to mark 3.67 or 26, excuse me, or 10/3, and that's at approximately x is 3.67. So how do I know whether this, first of all, if this is an inflection point, a change in concavity, and secondly, how do I know if it's a change in from going concave down to concave up or concave up to concave down? Well, I already know that if I test f double prime at a point and the output value of f double prime at that point is positive, then the function is concave up in that area. And if I find that it's negative, then I know it's concave down in that area. So I have to pick a point that's to the left of x is approximately 3.67. So I'm going to pick 0 because that is an easy point to evaluate the second derivative. And I get that 6 times 0 minus 20 is negative. And I don't really care about the value, I just care about the sign of it. Because if the sign is negative, then I already know from what we discovered back here that if f double prime of x is less than 0, then the function is concave down. So that allows me to now draw a segment on this interval that's concave down. Now you might be saying, well, how come I can test just one point in that interval? And the answer lies in the same answer to, well, why can I test a point to the left and to the right where the derivative is 0 to test whether that point is a maximum or minimum? Well, it turns out that the only way that we could change concavity is to, well, for one, have a second derivative of 0, and that's a point at which the derivative of the derivative, i.e. the derivative of a function, passes through 0. And if that's the case, then that must mean that either this function continues to be concave down or is a change in concave down to concave up. Now keep in mind that a function, for example, a first derivative could have a false maximum. So for the example, that point might be a critical point because the slope at that point is 0, but actually the function may not have a maximum at that point because it could have this sort of false maximum idea. We've got to test what the slope is on the left side, which is positive, and on the right side, which is positive, which tells us that that's not a max. Well, in a similar fashion, the derivative of the derivative, we have to check both sides to see if it changes signs. So what can I pick to the left, to the right of 3.67? I can choose, let's say, 4. That's a whole number, easy to evaluate. All I want to know is the sign positive or negative? Well, f double prime of 4 is 6 times 4 minus 20, which is 24 minus 20, which is positive. Okay, that's all I care about, is that the second derivative is positive, which means that the function is concave up on that interval. So in fact, I do have a change in concavity. And remember, all we're doing here is just trying to sketch something qualitative to show that it goes from concave down to concave up. So that critical point of the first derivative is a point at which we go from having concave down function to concave up function, and so this is an inflection point. And specifically, it's a function that goes from concave down to concave up. As always, we should always check this against a graph just to make sure, so let's do that. So here I have a graph of x cubed minus 10x squared plus 12x, and indeed it is concave down for a while, and then it turns to concave up, and it does appear that that happens somewhere between x equals 2 and x equals 4. So another thing I can graph here is I can graph the derivative, which we know is 3x squared minus 20x plus 12. And what does that tell me? Well, number one, anywhere the derivative is 0, that's where there's a either a local or global max or a local or global min. And I can see that there's a local min right here at x equals 6, which corresponds to that point. Great. I have a derivative of 0 when x is approximately 0.667. That's the local maximum here. But we haven't looked at the idea of plotting the second derivative. So if I plot 6x minus 20, first of all, what I notice is that that tells me something about the first derivative. So I'm going to ignore the first function for a second, and I know that the slopes go from decreasing. Here they're positive, 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 negative slope, negative slope, negative slope, negative slope, negative slope, negative slope, more and more negative, so that the slope function is decreasing until it hits this point right here, which is the minimum of the derivative, and then the derivative function begins to increase. So the slope is still negative, 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 but less and less negative, and then the slope goes to positive, 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 more positive. So I plot just these two functions, the original function and the second derivative of the function, and I click on that point right there. Well, that's 3.33, which is that's the same thing as I think I put in the slide. This is 3.67, but it's 26 is actually 3.33, and that is the point of inflection where the concavity changes right about there. Go from concave down to concave up. So good verification of that. And now let's take a look at another function, something a little bit more complex. We have a sinusoidal function, and we can again look for points of inflection, and we will do that. And let's go ahead and take this guy's derivative just to practice this concept. We know that the derivative of this will require a chain rule, since we have not just the sine of x, but the sine of 2x plus 8. So the derivative of sine is cosine of the guts multiplied by the derivative of the guts, which the derivative of 2x plus 8 is just 2. And so my derivative function is 10 times cosine times 2, which is 20 cosine of 2x plus 8. Now the derivative of that function, we know that the derivative of cosine is negative sine, so we have 20 times the negative sine of the guts multiplied by the derivative of the guts, which once again is going to be 2. So if I simplify this a little bit just to make it look cleaner, I have 20 times 2 is 40, and multiplied by a negative is going to make that negative 40 times sine of 2x plus 8. Now the question is, when does the second derivative equal 0? So that is, where are there potential inflection points? Well, we've got to be careful here, because now we want to set 40 times sine of 2x plus 8 equal to 0. So how do we do this? Well, first of all, let's get rid of the coefficient, divide both sides by 40. That eliminates that. We get 0 equals sine of 2x plus 8. And now I have to take the arc sine, or the sine inverse of both sides. So if I take the sine inverse of sine of 2x plus 8, I've got to take the sine inverse of 0 as well. Take the sine inverse of both sides. Have to perform the same operation. And so what do I come up with here? So we have to ask ourselves, where does this, for what angles or for what inputs is the sine function equal to 0? Well, if we sketch the sine function, then the sine function looks like this. That's just one period of the sine function. And the sine function, sine of x, and this is versus x, is 0 here, it's 0 here, it's 0 here. What are those points? Well, this is the point x equals 0. This is the point x equals pi. This is the point x equals 2 pi. And then again, this function repeats for all values of x. It's a periodic function. So again, I'll have another one at x equals 3 pi and x equals 4 pi. And so I will basically have infinitely many of these. So how do I write this? Well, the way I write this is where does the sine function equal 0? Have an output of 0. It has an output at 0 plus or minus pi. And not just plus or minus pi, but plus or minus any constant multiple of pi. So k can be negative, could be 0, 1, 2, 3, etc. Or it could be -1, -2, -3, right? Because this function continues on in this fashion over here as well. It's actually symmetric in terms of the points where it crosses the x-axis on the negative side. And so basically we have anywhere plus or minus k pi. Okay, well now the sine inverse of sine, if we take an inverse of a function, a function of a function, and the inverse of that function will just leave us with 2x plus 8. And so if we solve for x, then we get -8 plus or minus k pi equals 2x. And then if we divide that whole thing by 2, we get -8 divided by 2 is -4, plus or minus, k is a constant, so that's k over 2 times pi. All right, well, so the point here is that there are infinitely many of these inflection points. That in fact, if we go from concave up to concave down, concave up to concave down, concave up to concave down, at any multiple of -4 plus or minus k over 2 pi. So for example, one possible point that we should see an inflection point is, let's say k equals 1. So that means we should see an inflection point at, let's pick k equals 2 to make this more mathematically simple. -4 plus or minus 2 over 2 pi equals x, which that ends up being -4 plus or minus pi, which is approximately -4 plus or minus 3.14159. So let's take a look at the sketch of this function. So we'll go ahead and plot our original function, 10 sine of 2x plus 8. So I'll plot that 10 sine of 2x plus 8. And I can see that the inflection points seem to occur, somewhere around here, somewhere between this concave up portion, this concave down portion. So I'm going to plot the derivative, which is 20 cosine of 2x plus 8. So that, of course, tells me where the critical points are. And the critical points, of course, are there. What happened here? Apparently I just clicked on the wrong point. So there's a critical point right there at 0. And that's what we expect because we know that right there. That point right there, x equals -0.073, corresponds to the maximum on our 10 sine of 2x plus 8. And I'm going to go ahead and plot -40 sine of 2x plus 8. And I'm going to remove the first derivative. I don't need that anymore. And what we're arguing is that anywhere where the second derivative is 0, there's an inflection point. And that clearly seems to correspond to a point where our original function, 10 sine 2x plus 8, goes from concave down to concave up. So there's one at -0.858, and there's one at positive 0.712. Well, we argued that that would be -4 minus, let's see, we said minus pi, and that comes out to -0.858, which is consistent with this critical point here, and then one occurs over here as well. So because there are infinitely many of those, I can keep doing this. There's one right there, and there's one right there, and there's one right here. I have infinitely many critical points. So we've just got to be careful of that. If it's a periodic function like this, then it can potentially have infinitely many of them, especially where the concavity just continuously changes.